So section 6.5 takes us back to the world of matrices, and in fact we're going to learn in this section how we can use something called Cramer's rule in order to solve a system of equations in many instances. Not all the time, but a lot of the time we will be able to use Cramer's rule. But before we can use Cramer's rule, we have to learn about determinants. And every square matrix has a determinant, and we're going to begin with the simplest of the square matrices, a 2 by 2. So I've got this in this general form of a 2 by 2 matrix where my first row is a sub 1, b sub 1, and my second row is a sub 2, b sub 2. And note that I'm saying this is a matrix by showing the brackets around that rectangular arrangement of numbers. And the determinant of that matrix, and the notation is, it looks like absolute value bars have replaced the matrix brackets, right? And what that is, it is a real number that is defined in the following way. Every square matrix has a determinant, and for a 2 by 2 matrix, this is how I find that real number that's associated with it. I multiply across this first diagonal a sub 1 times b sub 2. So I always kind of think of it as I'm multiplying on a diagonal a sub 1 times b sub 2. And then I always subtract for a determinant. And then I'm going to go back this way and find the product going in that direction. So that's b sub 1 times a sub 2, and if I put them in alphabetical order, a sub 2 times b sub 1. So that's going to give me a real number, a single real number that's associated with that 2 by 2 matrix that I find by multiplying in this direction and then subtracting the product going in this direction. So another way of talking about it is to say that the value of that determinant is that difference that I find when I multiply a sub 1 times b sub 2 and subtract a sub 2 times b sub 1. And we're calling it a second order determinant because it came from a 2 by 2 matrix. So if I was finding the determinant of a 3 by 3 matrix, I would call that a third order determinant. A 4 by 4, a fourth order determinant. And we're going to practice doing these 2 by 2 determinants by hand, and then we're going to transition to using our graphing calculator to do higher order determinants because it gets quite complicated for matrices that are larger than 2 by 2. All right, so let's do this first example. And I want to find the determinant of this particular matrix, and another way I could do it is I could say determinant of negative 2, 3, 5, 1. And this is the notation that our graphing calculator is going to use, DET, for determinant. And I could also use this notation that looks like absolute value, right? And then I can go ahead and find those products, right? So negative 2 times 1 is negative 2. And then I always subtract, and then I go back the other way. And 3 times 5 is 15. And negative 2 minus 15 is negative 17. So that is that real number that is associated with that 2 by 2 matrix. All right, let's look at the next one. The biggest problem that students have with this is signs, so just be careful with your signs. I'm going to call this matrix B so we can talk about another way that this could be shown. I could say determinant of matrix B. I could say put the name of the matrix inside the determinant bars, or I could write it out. And then I'm going to find my product going in this direction. That's going to be a positive 3, right? Minus, and then I'm going to find my product going the other direction, and negative 2 times negative 4 is positive 8. And 3 minus 8 is negative 5. So it's really not terribly difficult to find the determinant of a 2 by 2 square matrix. We can also use technology to find the determinant of any square matrix, and this is going to be very helpful to us when finding determinants of matrices that are larger than 2 by 2. So suppose that I have matrix A, and it is 2, 3, 4, 1. I can enter this matrix into the calculator using the methods that we developed in section 6.3, right? And then finding the determinant is as easy as selecting the second matrix, right? Open up my matrix menu, and then I'm going to arrow over and select the math option. And when I do that, the first thing I can do is find the determinant. So I'm going to hit enter. I'm going to go back to my names, go back and then name and pick A, close parentheses and hit enter. And it's going to tell me that the determinant of that matrix is -10. And I made a quick video to show how this is done step by step. So first thing that you have to do is go second matrix, and you need to enter the matrix. Just to review, edit, and we want a 2 by 2. And then I'm going to enter the elements, 2, first row, 2, then 3, then 4, then 1. Okay, so now I need to quit. So second, quit. And then I'm going to go second matrix again, and I'm going to go over to math, and I'm going to choose determinant. Right there. Hit enter. And then I'm going to go back to matrix again, and I'm going to choose matrix A under the names, and then hit enter. And I can see that the determinant is in fact for that one, -10. So really easy to do, really probably more work for a 2 by 2 matrix than actually doing it by hand, but that is not where the genius of the graphing calculator comes in. Where the genius comes in is when you are finding the determinant of a higher order matrix. So if you want to find the matrix, the determinant of a larger square matrix, like a 3 by 3 or even a 4 by 4, there are tricks to doing a 3 by 3, but a 4 by 4 there's no trick. It just takes forever. So we can use a calculator to do it very efficiently, and I made a video of this 3 by 3 just to walk you through that as well. So what I do is no different. I have to go into my matrix menu and enter it. I called it C, so I'm going to select Edit 3 by 3. I'm going to enter all the elements, the first row, 4, 5, -1, second row, 0, -2, and 1. Oop, 4, sorry. And then 3, 6, and -3. And then I'm going to have to quit. So second mode gets me quit. And then I'm going to go back into my matrix menu and select math. I want to do the determinant. And I need to select from my names, matrix C, and hit enter. And I can see that my determinant is in fact -18. And that is much, much, much quicker than the process of finding the determinant of a 3 by 3 or larger square matrix by hand. All right, let's go back and talk about systems of equations again, because we're going to find these determinants are extremely helpful in solving a system of linear equations. But we're going to develop the method that's known as Cramer's rule, and I want you to see why Cramer's rule works as it does. And I have a general system of linear equations where you'll notice that the first equation has subscripts of 1. So a sub 1, the coefficient of x in the first equation has a subscript of 1, the coefficient of y, b sub 1, and then my constant c sub 1. And then my second equation has subscripts of 2 on its coefficients. I want you to notice that I also color-coded them, and the reason for that will be clear in just a minute. So we're going to use one of the methods that we developed in the last section, section 5.1, to solve this system. And we're going to do it by eliminating the variable y, and we're going to use the addition method. So thinking about this, if I want to eliminate y, then I need to have coefficients on these y's that are opposites, right? So I'm going to have to do 2 multiplications in order to get that. And in fact, if I multiply that first equation through by b sub 2, So let me go ahead and write that I'm going to do that. So I'm going to multiply b sub 2 times that first equation, a sub 1x plus b sub 1y equals b sub 2 times c sub 1. And if I multiply this second equation through by the opposite of b sub 1, go ahead and show that I'm going to do that, a sub 2x plus b sub 2y equals b sub negative b sub, or the opposite of b sub 1 times c sub 2. Then when I distribute, here I'm going to have b sub 1, b sub 2 times y. Here I'm going to have the opposite of b sub 1, b sub 2 times y, so that when I combine them using the addition method, the y's are going to be eliminated. So let me go ahead and do that distributing. So when I distribute, I'm going to put them in alphabetical order. I'm going to get a sub 1, b sub 2x plus b sub 1, b sub 2y equals b sub 2, c sub 1. And I'm going to do the same thing in the second. I'm going to distribute. So I'm going to get the opposite of a sub 2 times b sub 1x minus b sub 1 times b sub 2y equals the opposite of b sub 1 times c sub 2. All right, so now I have two equations that are equivalent, right, to the original equations that I began with. So I'm going to rewrite my system. And I'm going to have a sub 1 b sub 2x plus b sub 1 b sub 2y equals b sub 2 c sub 1. And then the opposite of a sub 2 b sub 1x minus b sub 1 b sub 2y equals the opposite of b sub 1 times c sub 2. And when I add, these are opposites, and so they're going to cancel out. And I'm going to end up with a sub 1 b sub 2x minus a sub 2 b sub 1x equals b sub 2 c sub 1 minus b sub 1 c sub 2. Okay, all I did was subtract these two, right? And because I don't know what the values of these coefficients are, I have to be very general and just say this term minus this term equals this term minus this term. Now I have a common factor of x, right? There's a common factor of x, and I'm going to go ahead and factor that out. And I'm going to be left with a sub 1 b sub 2 minus a sub 2 b sub 1. And that's equal to b sub 2 c sub 1 minus b sub 1 c sub 2. And then if I divide both sides by a sub 1 b sub 2, a sub 2 b sub 1, a sub 1 b sub 2 minus a sub 2 b sub 1, these are going to divide out. And I'm going to get that x is equal to, going back to my colors, b sub 2 c sub 1 minus b sub 1 c sub 2 c sub 2 divided by a sub 1 b sub 2 minus a sub 2 b sub 1. Okay, so yeah, that was a lot, right? I want you to consider, though, that if I form a determinant like this, where I've got in the first column of that determinant the coefficients of x for my system, and the second column is the coefficients of y from my system, and I find my determinant, multiply this way minus this way, I'm going to get a sub 1 b sub 2 minus b sub 1 a sub 2. And where do you see a sub 1 b sub 2 minus, in other words, a sub 2 b sub 1? Why, it's in the denominator of my solution, isn't it? So I could begin to rewrite my solution using that determinant in the bottom, a sub 1, a sub 2, b sub 1, b sub 2. In other words, if I form a determinant using the coefficients of my variables when my system is written in standard form, that's going to be the denominator for solving for x. Now, notice that if I replace in my determinant the coefficients of x with the constants, right? So I'm replacing the coefficients of x with the constants, c sub 1, c sub 2. I'm leaving the coefficients of y alone. If I form the determinant of that, right, if I evaluate that determinant, then I'm going to end up with c sub 1, b sub 2 minus b sub 1, c sub 2. That is in my numerator of my solution for x. And so I could replace that expression with that determinant, c sub 1, c sub 2, b sub 1, b sub 2. And so that is going to be a general method for solving for x using something called Cramer's rule by finding determinants, right? So in general, our solution for x is given by that quotient of those two determinants. And we could use the same addition method again to solve for y, but I will spare you that. And you will end up with y is equal to, my denominator is not going to change. It's still going to be the first column is coefficients of x, the second column is coefficients of y. However, when I'm solving for y, I'm going to replace the coefficients for y with the constants and leave the coefficients for x alone. This result is known as Cramer's rule, and we know how quick and easy it is to find the determinant of a 2 by 2 matrix, right? So let's summarize it on the next page. So solving a system of linear equations in two variables using Cramer's rule, this summarizes what we just did, right? It just adds a little bit of new notation in that denominator that involved the coefficients of the x, right, and the coefficients of the y, right? We're going to call that determinant D, capital D. That's going to be our denominator. And as long as that is not 0, we can use Cramer's rule to solve the system. If it is 0, then what that's going to be telling us is that either the system is inconsistent and there is no solution, in other words, the lines are parallel, or the system is made up of dependent equations in which there are an infinite number of solutions. And so in either instance, that denominator will turn out to be 0 and Cramer's rule cannot be used, which is why we needed those other methods, right? Now, again, the numerator is made up of the constants, right? And where the constants are found in my determinant depends on if I'm solving for x, in which case they replace the coefficients for x, or y, in which case they replace the coefficients for y. So that is Cramer's rule. Now let's do a couple of examples of this for two equations and two unknowns. And we're going to see that, yeah, it's a little more tedious, but sometimes there's a bigger payoff for that work, particularly if my solutions involve fractions. And then especially if we want to solve a system of 3 equations and 3 unknowns, which we didn't even do using other methods. But the process would have been the same, it just would have been much more tedious. Then Cramer's rule is especially helpful. So in order for me to use Cramer's rule to solve this system, I need to the first step is always going to be to find that denominator and see if it's 0. So remember that that denominator d is made up of the coefficients of the x variable in the first column and the y variable in the second column, right? And notice too that my equations have to be written in standard form, ax plus by equals c, right, in order for me to do this. So I've got 2, 1, and negative 3, 2. And I'm just going to do this one by hand. I'm not going to get my calculator out. So 2 times 2 is 4, minus, always minus, negative 3 times 1 is negative 3. So 4 minus the opposite of 3 is the same as 4 plus 3, which is 7, which is not 0, so I can use Cramer's rule. Now I'm going to find that determinant that's going to help me solve for x, which the notation is d with a little subscript of x. And I know that I am going to replace the x variables, the coefficients of the x variables, with my constants, which in this case were negative 11, and 12. And I leave the y alone, so negative 3 and 2. And so I'm going to multiply this way and get negative 22. Minus, always minus, negative 3 times 12 is negative 36. And so that's negative 22 plus 36, which is 14. And then I'm going to find the numerator to solve for y, which I'm going to call d sub y. And that one, I replace the y coefficients with the constants and leave the x alone. So 2, 1, and then negative 11, 12. So multiplying, I'm going to get 24, right? Minus negative 11, or 24 plus 11, which is 35. And then x is simply equal to d sub x divided by d. 14 divided by 7 is 2. Y is equal to d sub y divided by d. 35 divided by 7, or 5. And so my ordered pair solution to this system is 2, 5, using Cramer's rule. And yeah, you probably could have done that one a lot quicker by using the addition method, but we're practicing Cramer's rule for when we want to have it at hand, okay? So let's do another one. So this one says, if possible, use Cramer's rule and technology to solve the system. And what we're going to do is we're going to first take our system and put it in the proper form, because neither of these equations is in standard form. So I need to subtract 3y from both sides on this one, and that's going to give me 2x minus 3y equals 4. And then on this one, I'm going to add 5y to both sides. So I'm going to end up with 4x plus 5y equals 3. Now I've got them both in standard form. So first thing I'm going to do is evaluate my denominator d to see if it's not 0, right? And I'm going to color code this. I am going to be putting my coefficients of x in the first column, my coefficients of y in the second. So that's going to be 2, 4, negative 3, 5. And you can use your calculator and practice with this. In either case, whether you do it by hand or with the calculator, you're going to get the result of 10 minus negative 12. 10 plus 12 is 22. And then this is not 0, right? So we can use Cramer's rule. So now I'm going to go ahead and I'm going to find the determinant that's going to go in the numerator to solve for x. And I know that I replace the coefficients of x with the constants when I'm solving for x, and I leave the y's alone, right? So that's going to be 4, 3, and negative 3, 5. And then that's going to be 20 minus negative 9. 20 plus 9 is 29, okay? And, if you're using your calculator, you should get the same thing. And then I'm going to find the numerator for the fraction that's going to solve for y for me. And this time I'm going to replace the coefficients of y with my constants and leave the coefficients of x alone. So that's going to be 2, 4, and 4, 3. And I'm going to get 2 times 3 is 6, minus 4 times 4 is 16, negative 10. Okay, so now this is where Cramer's rule really does shine, because x is equal to d sub x divided by d, which is 29 divided by 22. Okay, that is not a nice number. It's a rational number, right? But it's not one that I could find a decimal representation for because it's non-terminating. And if I get that for x, then I've got to plug it into one of my original equations to solve for y. And I don't know about you, but that does not sound fun to me. Instead, I can just say y is equal to d sub y divided by d, negative 10 divided by 22. And if I simplify that fraction, I'm going to get negative 5/11. So my ordered pair solution to this system using Cramer's rule is 29 22nds and negative 5/11. Now that would have been much more difficult, much more tedious, maybe not more difficult, but more tedious to do using either elimination or substitution. And once we got to the value of either x or y, that would have involved plugging a fraction and solving for the other variable. I'd rather do Cramer's rule for this, particularly if I'm using my calculator to evaluate these determinants. We can extend this work we did with a system of 2 equations and 2 unknowns to solve larger systems. So in general, a system of 3 equations and 3 unknowns is going to look like this. A sub 1x plus b sub 1y plus c sub 1z equals d sub 1. All the coefficients of the first equation. And then I'm going to have 3 unknowns in my second equation. A sub 2x plus b sub 2y plus c sub 2z equals d sub 2. And then finally a sub 3x plus b sub 3y plus c sub 3z equals d sub 3. So 3 equations and 3 unknowns. Now you can use the methods that we developed in section 5.1, the substitution and the addition method, in order to solve a system that's larger than a 2 by 2. This would be a three equations and 3 unknowns, right? You can do it. It's a lot of work, but we can extend the work we did with the 2 equations and 2 unknowns to solve them using Cramer's rule in much the same way. Notice that instead of just a matrix D, D sub x, and D sub y, I'm going to have D, D sub x, D sub y, and D sub z. But what I'm doing is following the same pattern. So my denominator are the coefficients of all the variables x, y, and z. That first column, the coefficients of x. The second column, the coefficients of y. That third column, the coefficients of z, right? And d sub x, I'm going to replace the coefficients of x with the constants on the right side. So those are the constants. These are the coefficients of x, y. These are the coefficients of z. When I'm solving for y, I replace the coefficients of y with those constants and leave the x and the z alone. And when I'm solving for z, I replace the coefficients of z, all right, with the constants and leave the coefficients of x and y alone. And then again, if the denominator, if this d is 0, Cramer's rule cannot be used, and you have to use other methods. But if it can be used, it is so much more quick and easy than any of the other alternatives. All right, so now let's look at an example, and it says, if possible, use Cramer's rule and technology to solve the system. So I definitely want to use technology because I don't want to have to evaluate those third-order determinants without it. But before I can do that, I need to figure out what those determinants are going to look like, right? So D is going to look like all of the coefficients of x, y, and z. So my coefficients of x are going to be 1, 1, and 2. So 1, 1, and 2. Coefficients of y are going to be 2, 4, and 3. So 2, 4, and 3. Coefficients of z are going to be negative 1, negative 2, and 1. So negative 1, negative 2, and 1. And if I enter that 3 by 3 as a 3 by 3 matrix into my calculator and then evaluate the determinant of that 3 by 3 square matrix, it turns out to be equal to 5, which is not 0, which means we can use Cramer's rule to solve the system. So at this point, I'm going to go forward and I'm going to find d sub x by simply trading out that first column with my constants on the right side. So negative 4, negative 6, 3, 2, 4, 3, negative 1, negative 2, 1. Enter that into my calculator using another matrix, maybe B this time, and hit determinant of B, and whatever you want to call it, it doesn't matter. That's going to turn out to be negative 10. And so now I know x is equal to d sub x divided by d, negative 10 divided by 5, or negative 2. Now I'm going to solve for y. And to do that, I'm going to leave the coefficients of x alone, and I'm going to replace the y coefficients with the constants, and I'm going to leave z alone. Enter that into my calculator, whatever matrix I choose, determinant of that matrix. That turns out to be 5. So now I can solve for y. It's d sub y divided by d. It's 5 divided by 5. It's 1. And then at this point, if you want, you could plug x and y into one of those original equations and solve for z. Or you can, if you would prefer, go ahead and evaluate d sub z. So I'm going to replace, leave the coefficients of x and the coefficients of y alone, and I'm going to replace the coefficients of z with my constants. Enter that, use my calculator to evaluate that determinant, and it's equal to 20. And so z is d sub z divided by d, which is equal to 20 divided by 5, or 4. Okay, so the ordered triple solution to this system is x, negative 2, y, 1, z, 4. And if I wanted to check to make sure I had found a valid solution, I could plug that back in to each of those 3 equations in turn and verify that it in fact does satisfy them all. And so by evaluating at most 3, maybe 4 determinants, right, you can solve that system of 3 equations and 3 unknowns using Cramer's rule as long as that determinant in the denominator is not equal to 0. And with technology, that makes pretty quick work of solving that system.